Welcome everybody to the next presentation in the Microsoft Research Summit 2021. My name is Dragomir Radev from Yale University, Department of Computer Science. And today I'm going to be talking about some recent projects in our lab on closing the loop in natural language interfaces to relational databases. And I'll be talking in particular about our work on parsing, dialogue, and generation. So, as you know, a lot of the natural language interfaces that are currently in existence deal with unstructured text, such as images and videos and web pages. Here we are focusing mostly on the items in this purple box, which is databases, knowledge graphs, and tables from Wikipedia. So while we would ideally want to be able to build systems that understand human language, we still have to convert those natural language questions into SQL queries. For example, select quantity from product where name is hoverboard X10. Obviously, the users of the system don't understand SQL, so we still want to be able to allow them to ask their questions in natural language, like, for example, how many hoverboards are left in stock, and then our system needs to convert those into SQL queries. So today I'm going to talk about three recent contributions to this project. One is about understanding the user better. This involves semantic parsing and text to SQL. Then understanding the data in the tables by doing pre-training of tables. And finally, responding to the user in the form of answering questions, structure to text natural language generation, and summarization. So to give an idea, if you have a natural language question like this one here, there are certain words in it that trigger different components of the matching system in different ways. So the four ways are European and Australian Open are shown in red. Those correspond to actual values in the table. The text in green corresponds to column names or attributes. The text in blue corresponds to table names. And finally, the text in purple corresponds to logic snippets, which have to infer some information that was not explicitly said in the table. So our first contribution to this project was a dataset called Spider, which was the first dataset for text-to-SQL generation that has multiple tables joined with foreign keys. Also, different SQL patterns, for example, min and max, aggregate commands, and also nested queries. So it has 10,000 questions, 6,000 unique SQL queries, and 200 databases from 138 domains. The only existing dataset before that was WikiSQL from Salesforce, and the difference between the two is that WikiSQL was only about single tables and didn't have any of those complicated additions. So Spider was built by students in our lab, and it took an enormous amount of time to build it and to clean it and to verify all the data points. So the data here is divided into four categories: simple queries, medium, hard, and extra hard queries. So we have a leaderboard for performance on the Spider dataset. As you can see, we went from a very low baseline performance 3 years ago when this project started, so it's something in the order of 10 to 18 points on the dev test. And now, most recently, we've been getting very high performance submissions, most recently from ACL 21 by a group from Shanghai Jiao Tong University and AI Speech. As you can see, we have a huge improvement in performance slightly over 3 years. The second data set that we created for this project is called SParC, which is an extension of Spider to dialogue. As you can see here, we have a user interacting with a database and the corresponding SQL statements. There is also a leaderboard where the best performing system is a combination of Yale, Microsoft Research, and Penn State University that uses RADSQL and SCORE. The third data set that we created is called CoSQL, and this is about dialogue state tracking using SQL. So here we have the different dialogue states and the corresponding SQL statements. So again, this is a data set that people use to evaluate their systems. And as of the time of this presentation, the best performance is again from the Yale/MSR/Penn State University team. Okay, now I'm going to switch to the second part of this presentation, how we pre-train a language model from tables. I mean, everybody knows that current language models such as BERT and RoBERTa achieve extremely high performance on different question answering and other natural language processing data sets. However, they're only trained on text such as Wikipedia, articles, and books. Now, if you remember this example, in order to get high performance on tables, we need to do some additional things which cannot be inferred from plain text alone. So this is encoding the table content, jointly understanding the questions and the tables, and then figure out how to use compositionality and logic to put everything together. So one of the first ideas that we had, since we don't have a very large amount of training data, was to use data augmentation in the same way that this has been used in the past, more notably by Jia and Liang and some other more recent papers. So in that case, what they do is they look at some examples from the training set, then they induce a synchronous context-free grammar, which is then used to generate some additional examples from the same distribution. So this approach works pretty well in certain cases, but it turns out that it doesn't work well in the task that we are considering. So we did an experiment where we compared the performance of systems with and without such synthetic training data on 5 different data sets, so Spider, SParC, and CoSQL, and also different multi-was data sets such as trade and SumBT. As you can see, comparing the blue bar and the red bar, not only doesn't performance improve when you add the synthetic training data, but in many cases it actually falls down, and in bottom line is that we cannot use this data set to improve the training process. So instead what we're doing is slightly different. We're building a system that has a compositional inductive bias that is specifically designed for tables. So in order to do this, we have first, again, annotated text-to-SQL examples. We have a synchronous context-free grammar that is inferred automatically. And then we use this grammar to generate the sequence examples. And then we use this on some sample tables. So this is similar to what people have done in the past with data augmentation using grammars. Now, in addition to this, we have an additional component which uses RoBERTa as the language model. So here's how this works. In the first stage, we convert the SQL statements into different semantic representations for the different words. And then we train this using 475,000 synthetic text-to-SQL examples. So this gives us an objective function that we call semantic prediction loss. Now, in addition to this prediction loss, we use another objective measure, which is called masked language modeling, just like in other pre-trained language models. And then when we combine those two together, we get performance that actually improves on the state of the art. So in order to evaluate this approach, we use 4 different evaluation data sets. 2 of them are fully supervised and 2 are weakly supervised. In the fully supervised semantic parsing task, we have examples of both the input sentence and the output SQL statement. In the weakly supervised examples, we have sentences and the answers, but we don't have the actual SQL statement that we want to learn, so we have to treat it as a latent variable. So now I'm going to show you the performance of the system on different data sets. So first of all, we are comparing state-of-the-art system on the Spider data set, which at the time of this paper was RAD-SQL. As you can see, we have a performance in the high 60% using RAD-SQL, but then if we add our 2 metrics for improving the performance, we get an improvement of about 3.7 to 4 percentage points. Now I'm going to show you 4 other experiments with this data set. So first one is on fully supervised WikiSQL. In this case, we did 2 experiments. In the first one, we are comparing our system with both objective functions against the state of the art, and we get some nice improvements of around 1.6%. Now, what's more interesting is that if we limit ourselves to a random sample of 10K examples, then our performance improvement over RoBERTa large is even better, so in the order of 2.7 to 3%. So this is this bottom picture here. The second evaluation is on Wikitable questions. We see a very similar pattern. We get state-of-the-art performance by combining our system with GraPPa. And then we also do an experiment with 10% of the training data, and we get an even better improvement of 3.9% on the test set over RoBERTa. The third evaluation is on weakly supervised WikiSQL. As you can see, we again have a nice improvement in performance over the state of the art. Okay, now let's move on to the next part of this process. We want to be able to generate sentences that are grammatical and faithful and fluent based on the results of a SQL query. So let's look at an example. Here we have a list of a table of cars, different makes and models, and also their fuel efficiency. Suppose now that we have a question that says which cars get more than 100 miles per gallon. The corresponding SQL statement is select name, year, powertrain, highway from vehicles where highway is greater than 100. This gives us 4 different results. The best performing car here is the Chevrolet SParC EV, which gets 109 miles per gallon. Now suppose that we want to convey this result to the user. So for example, we want to build a sentence from this last record here that says that the 2013 Nissan Leaf electric vehicle gets 102 miles per gallon. So in order to do this, we have to pre-train a system that can generate text from structured data. So in order to do this, we built a data set that is called Dart, which starts from tables from Wikipedia tables. And then we build a taxonomy, like the one that you can see here, that tells us which attributes are related to which other attributes. So in this particular case, we can see that capacity is a property of stadium, open is also a property of stadium. Stadium is a property of team, city is a property of team, and in addition to this, we can also incorporate the table context and also the table title itself. Then we select a subtree from this ontology, and we build RDF triples that contain information from the table. So here we have 2 examples. In the first one, we say that the Amsterdam Admirals is a team that plays on Olympic Stadium. And then we have another triple that says that the Olympic Stadium was built in 1928. So this is the input plus the taxonomy, and the output is the sentences that are generated from it. So in our data set, we created a large number of what we call darts, which are the training samples. In this particular case, we have 2 examples, one with 2 triples and one with 6 triples. So we did some experiments using Dart. With the best performance that we got on all the different relevant evaluation metrics was using T5 large, which outperformed every other system. And we also did an experiment on Web Energy 2017, which is a standard structured data to text data set. And in this case, again, it turns out that using T5 large augmented by Dart gives us the best performance. Now, the next thing that we're doing as part of this project is to build a question answering data set over tables. So in this data set, which we call Feta QA, we start with a table and a natural language question that corresponds to a certain area of the table. And then we have crowd workers produce the answers in the form of actual sentences. So in this case, the question refers to the title of the table, also to 2 of the different attributes, and then we want to be able to compare the different records and do some additional logical transformations, for example, averages and mins and maxes. So this data set is different from previous question answering data sets because for the first time we have an answer format that is free-form text from Wikipedia tables. Previously there were data sets that do one or the other. Either you can have free-form text from some other data sets, or you can have Wikipedia tables but with short form, just factual answers and not full text. Now, the next thing that we want to do, which is something that we started working on a few months ago, is to summarize tables. And summarization in this context can be done in 2 different ways. You can either summarize the results from the query, or you can summarize the entire table. So in this particular case, what we want to do is not just to generate a sentence like the one that I showed you earlier, but to be able to summarize the entire result table and say that we have 4 vehicles that get more than 100 miles per gallon, and then possibly enumerate them or point to them in the table. So for this project, we've been collecting summaries of tables using a crowdsourcing interface. So those are some of the examples. From each of the tables, we have multiple summaries. And then we also have an interface where we show the users the structure of the table, the data in the table, and also the different summaries, and we ask the users to evaluate the quality of those summaries. Okay, so now I'm going to wrap up. As I showed you in this presentation, we have a very active research project on table-to-text interfaces and also on semantic parsing. The main contributions have been posted in the main conferences in the last few years. So first, the contributions on the semantic parsing side, then on pre-training for tables, and then finally on generation from tables. So let me thank you for your attention. And I would like to give credit in particular to Tao Yu, who just finished his PhD at Yale and moved to the University of Hong Kong, and also to all the other co-workers for this project. Thank you again, and bye.